Go over some more Gauss's law examples in detail. So this is just going to be all examples. Okay, so we're going to do a problem we already know the answer to again, but we're testing out Gauss's law to make sure it works, and we're calculating this in a different way because we already did this once with Coulomb's law, and when we did it with Coulomb's law, we had to calculate it using this long integration process. So this is going to be a much, much faster, easier thing because we don't have to write out a vector integral at one point and then extrapolate and take limits to infinity and so on and so forth. So we want to figure out the electric field of an infinitely long line of charge. And as I said before, very hard to draw infinitely long things, but we're going to just start by creating this line. You just have to imagine it being infinite, okay? And of course, because this is an infinitely long line of charge, it has electric field lines that point out in all directions. And these are not perfect, but you get the general idea. Okay, and we want to figure that out by choosing a Gaussian surface. Now, as we talked about earlier, and remember this is three-dimensional, so there's also lines pointing out and lines pointing into the page, and sort of it goes out in a circle in all directions. So in order to, I guess you could kind of like say these are also going back, and then there's some coming forward. That's the general idea, okay? So a Gaussian surface, the one we want to choose for the infinitely long line, looks like a cylinder. So I'm going to draw the cylinder. So this is our Gaussian surface. And once again, since this is a line, it's a two-dimensional or one-dimensional object, and you can't really be inside the line, so we don't have to worry about what's going on inside the line. But you can see the cylinder sort of starts here and ends here. So that's our line of charge. Now, the line of charge has a charge density, which we'll call lambda, okay? It's uniformly distributed, and remember, we have to go back to what we know the answer is, which is that we know that the electric field for an infinite line is 2k lambda over r. And we know this because we calculated it with Coulomb's law. And we integrated, okay? But now we're going to do this with Gauss's law, so we'll write Gauss's law here. Remember, this is E dot dA is equal to Q enclosed over the constant epsilon naught, which is 8.85 times 10 to the negative 12th. Now looking at these electric field lines and matching them with the electric field vectors, you can see at this point, right, at the top and bottom, the area vectors point up and down. At the sides, the area vectors point out, okay? If you want to deal with the electric field vectors, at this point, the electric field vector is perpendicular. At this point, the electric field vector is perpendicular. And along the sides, the electric field vectors are parallel. So using our, and you don't have to go through all these steps every time, but if you want to calculate this part, that means you need basically three, one for the top, one for the bottom, and we're just going to say top and bottom. Plus the sides. And this is still equal to Q enclosed over epsilon naught. Remember, the electric field is this, and the area is from the Gaussian surface. Because this right here is perpendicular on the top and on the bottoms, we can make that 0 because the dot product gives us 0. Then we just have this part of the equation still. And that comes over here. We know that because these are parallel, that's an angle of 0, so the dot product goes away. We also know that every electric field vector on this side surface, since it's the same radius, it should be the same electric field. So we can pull the electric field out because it's constant. And then we have dA for just the cylinder is equal to Q enclosed epsilon naught. And we'll get to Q enclosed in a minute. But we know the area of the outside of a cylinder, and that since we're integrating over that whole surface, and let me just sort of color that in. We'll make it orange. So just the round part. Because of that, we know this is going to be E times 2 pi R, where this is R, and we'll say this is L, is equal to Q enclosed over epsilon naught. And these are still our electric fields. The Q enclosed, that part, let's pick a color, is just the charge in here. So this would be length L. So if we want to figure out Q enclosed, that's going to be equal to the charge density times the length. Okay, so this becomes E times 2 pi R L lambda L over epsilon naught. You can cancel some things. Oh, and also just as a side note, this becomes this. And we can cancel some things, so L and L should cancel. This is the same L. And this gives us E is equal to this R should be lowercase r. Quick adjustment. Now, why is this R lowercase r? Well, it's lowercase r because this is the Gaussian surface. So this can be as big or as little as you want it to be, meaning this is an adjustable imaginary thing, so you can make it bigger or smaller. So we want to indicate that r is a variable. Okay, so this becomes lambda over 2 pi r epsilon naught. And you'll say, okay, this doesn't quite look like the thing that we were dealing with before. But remember, K is equal to 1 over 4 pi epsilon naught. So converting this to K, then our E becomes 2, because remember there's a 2 in the denominator, so we'll pull a 2 out to get a 4. K lambda over R, and this is the same. This is the same as this, the one we found before. So Gauss's law worked, and instead of doing a whole integral, we just had to do some strategic geometry, okay? Okay, so we just did a line of charge, but let's do an infinitely long cylinder, all right? So the infinitely long cylinder, we're gonna just sort of draw a section of it, since it's very hard to draw an infinitely long cylinder. Oh, that's not right. Ooh, getting some drawing tools. So since this is a three-dimensional object, it's going to have a radius r, and that's capital R because it's constant. I'm going to try not to screw that up this time. And a uniform charge, volume charge density rho. And it's a volume charge density because it's a three-dimensional object. I'm going to make 2 copies of this because we're going to use it twice. Once because we want to calculate the electric field inside, and once because we want to calculate the electric field outside. So this will be 2 separate Gauss's law problems. So we're going to start with the electric field outside because that one's going to look pretty familiar. And for that, we are going to need a radius for our Gaussian surface where r is greater than capital R, where this is capital R. Remember, our Gaussian surface we're going to represent with this yellow thing. So we'll draw our Gaussian surface as a cylinder that goes around the cylinder we already drew. Right, so it kind of goes through that guy. And this is also filled in, so oops. So it sort of captures part of this cylinder. Remember, this is just the surface. Oops, I'm not doing a good job of this. This is terrible. Okay. Now, because this is a Gaussian surface and it can be any radius, I'm gonna do that in gray so you can see it better, greater than r, this is going to be little r. Okay, so that's this radius, little r. And this, we'll say this thing has a length of L as well. Okay, so starting from Gauss's law, which is a closed surface integral of E dot dA, Q enclosed over epsilon naught. Remember, this comes from Gauss. This comes from our electric field. We know that just like before, we should have the top and bottom of the cylinder are going to have area vectors that are perpendicular to the surface vector. I mean, not the surface vector, the electric field vector. So the dot product goes away for the top and bottom of the cylinder. So you can get rid of that. So this becomes just the sides. We'll just say sides. We'd get rid of the circle because this is no longer a closed surface integral of E dA, because remember the dot product on the sides, you have electric field vectors that go this way, and also area vectors that go the same way. So that's parallel, the dot product goes to 1. Q enclosed, that's going to get a little more complicated here. Let me do it in blue. This is the total charge enclosed. It's just this part of your actual physical cylinder that's inside the Gaussian sphere. And we do that with our density. So remember, our density is going to be rho. Okay, so density, let me just work on this for a second. Density is given as rho. Oops. So if you want to get Q enclosed, whoops, that's going to be equal to rho times the volume enclosed. Now the volume enclosed is not the volume of the Gaussian surface, it's the volume of that thing that's blue, right? So it's the chunk of the physical cylinder that's enclosed by the Gaussian surface. So that means this radius, the blue radius, is still big R. Okay, it's the same as the radius of this thing. And so then you need the volume of a cylinder, but just with these dimensions. So we have rho, and then we have pi big R squared times L, and that's the blue part. And then the rho comes from the red. Okay, so our Q enclosed ends up being rho pi capital R squared L. And it's very important that it's capital R because it's not little r. Little r encloses more than just the cylinder. Okay, so we pull out E, and then we end up with dA for just the sides, not the top and bottom of the cylinder. And we have rho pi R squared L over epsilon naught. So the area of the surface area of just the sides of a cylinder, that's going to be 2 pi. Now it's little r L, and that's little r because we're looking for this yellow thing, right? This is just the yellow part, excluding the top and bottom, but we're not going to go into that again. That's in the previous example problem. And then this becomes rho pi R squared L over epsilon naught. So you'll notice once again that L is going to cancel. We also can cancel the pi, and we end up with E is equal to rho R squared over 2 epsilon naught, and then this is 1 over R. And I'm making that separate because everything else is a constant. So this is for outside or R greater than big R. Okay. Now that seems pretty straightforward. It looks a lot like, so this is just a constant, and then we have an inverse relationship between our electric field and our R. So we'll call this out. So we still need to do the inside, and we're going to expect the inside to be something more like linear because we're going to enclose more and more charge. And so I'm going to draw this. So here we can draw our Gaussian surface, and let me just say, this is for the inside, meaning R is going to be less than big R, okay? And we can make these less than or equal to, and I can show you what that means in a second. But inside, we're going to start with the same Gauss's law, E dot dA is equal to Q enclosed over epsilon naught. But our Gaussian surface is now going to have to be drawn to be inside the cylinder. So we draw sort of a tiny cylinder, maybe not that tiny, a tiny cylinder inside our big cylinder. Okay, and this tiny cylinder has a radius little r. Okay, and so once again, we have E, we have dA, and then we have to figure out what Q enclosed is, and that has to do with just what's enclosed inside, and we'll get to that in a second. But just like before, E pulls out, whoops, do the wrong color. E pulls out for the reasons that we've talked about in a cylinder before. On the sides, we have area vectors that are parallel to the electric field vectors. On the top and bottom, we have perpendicular, so the dot product goes away. So we end up with E dot dA for just the sides of the cylinder. And then we still have Q enclosed over epsilon naught. As for our Q enclosed, in this case, it's equal to rho times V enclosed, and in this case, V enclosed is just the same as the Gaussian surface, because the Gaussian surface encloses all the charge, there's no empty space in there, so that becomes rho times pi little r squared, and this is a key difference, right? Because before we used big R because we enclosed the whole radius and then some empty space, which we didn't want to include because it didn't have any charge in it. In this case, we're just enclosing this and we don't get all the way to the edge, so there's no empty space, okay? And remember, once again, rho is a material property of the original physical object, which is an infinitely long cylinder. Obviously, hard to draw infinitely long cylinders, but we drew a really long one that we could fit on the page, okay? So this becomes E times the area, the surface area of a cylinder, which is 2 pi little r, because remember this is the Gaussian cylinder, times L, and we know it's the Gaussian cylinder because it's not infinite. And then this becomes rho pi little r squared L all over epsilon naught. Okay, once again, we're getting rid of the pi, we're getting rid of the L, but in this case, we're also getting rid of some R's because the key is always which R are you using, and you have to be very careful there. Okay, so now E on the inside is going to be equal to rho over 2 epsilon naught R. Okay, so this is E, our electric field inside, meaning R is less than big R. Okay, so if you look at these, here E has an inverse relationship and here E has a linear relationship. If you want to plot that like we did before, here's E versus R, you're going to have a linear relationship and then an inverse, sort of like we did before. It's not inverse squared, so it shouldn't be quite as steep. But this boundary condition is going to be R, and then when this is equal to R, this point, this maximum point of this maximum electric field is right at the edge, right at the surface, right here. Okay, so over here, you're going from here to here, so from 0 to big R. Okay, and then once you get outside, it's essentially from R to infinity, which is hard to draw also, and that is where you have your inverse relationship. But right at the boundary condition, you get an electric field that's rho capital R, which is a constant radius, over 2 epsilon naught. And so this is what your graph of electric field from the middle of the cylinder all the way out to infinity should look like. And last but not least, we have this problem for our Gauss's law basics, where we're going to calculate the electric field due to the infinite plane. And just a side note, when I was taking this class at Berkeley, I had a professor who was a native Russian speaker, and whenever he talked about the infinite plane of charge, he called it the infinite sheet of charge, which is a very good substitution. But unfortunately, with his accent, he spent a lot of time telling us about the infinite sheet, which was unintentionally hilarious. So now I can't really do any problems about the infinite sheet of charge without laughing. So I will walk you through this. This is and once again, we know the answer from doing Coulomb's law, and just generally we've sort of established this, that the electric field due to the infinite sheet or infinite plane, is eta over 2 epsilon naught. And also, if it's a capacitor, you just get rid of the 2 because remember, a capacitor is 2 infinite sheets. So here is the infinite plane, and I'm going to have to draw it finite because I can't draw infinite things, unfortunately. Not one of my skills. And so we're just going to color this in, and it's a two-dimensional, just a surface, right? It doesn't have any thickness, which, you know, is a little unrealistic, but for the sake of mathematics, we're going to do it that way. We know, of course, that the electric field points up above it and down below it, and it's more evenly spaced than that, but you get the general idea. So I guess I'll draw a couple more. So anyway, we have to deal with Gauss's law for this. So here's Gauss's law, which means we have to pick a Gaussian surface. And of course, we are, you know, you can choose any surface, any closed surface, but of course, we pretty much only ever choose 3, which are sphere, cylinder, box. And in this case, because it's an infinite sheet, we're going to pick a box. And so the box looks something like this. I think I can draw that better. Okay, let's do it with the right color. So here's our box. So you get the general idea. That's the box. We're going to fill it in because it's just the surface, right? It's a hollow box. All of these Gaussian surfaces are just surfaces. They're empty. Okay, but they have a surface area, and that's what that is. Okay, just like before, we know that each side of the box has a dA, and so the only place where dA is parallel to the electric field would be the top and bottom of the box. And because we know that the electric field is constant, well, that puts us in a position to deal with the dot product. So remember, when we separate this is a closed surface integral, into a bunch of surface integrals. There are 6 sides to this box, and we're only including 2. I'm not going to write that all out right now, but essentially we have 2 times the top or bottom electric field, which is constant, so that means we can pull that out. dA, the dot product goes away because of the parallelness, and then we have Q enclosed over epsilon naught. So we end up with 2E dA, where this is the box top, over Q enclosed epsilon naught. Remember, this is E, this is our dA. And so actually, just to be clear, let's do this in green. You're just integrating this top, and we're doing the top and bottom, but because we just multiplied it by 2, we only have to do 1. So, because we know they're the same. So this becomes 2E, and then we know that this, let's say this box has sides L, right? So we'll call that L squared. And then we actually need to think about Q enclosed. And Q enclosed, let's use this blue one, is just the part of the charge enclosed by that box, right? So just the chunk of the infinite sheet, so the finite square of charge. And because we know that this thing has a charge density, right? That means Q enclosed is equal to volume enclosed times the charge density. Oh, sorry, not volume. This is an area because it's only 2 dimensionals. Area enclosed, which is the blue thing. Whereas this N, eta is a squiggly N, is from the actual infinite sheet. So area is L squared, okay? So this becomes eta L squared over epsilon naught. You can see it's good since it's infinite, you can cancel the L squareds, so they go away, so it doesn't matter how big or small of a box you choose, you end up with the same thing no matter what, because these L squareds are always going to be the same. And this gives you E equals eta over 2 epsilon naught, which is what we were expecting for the infinite sheet from our original calculation that we used Coulomb's law for. So let's talk a little bit more about capacitors. All right. Now a capacitor is essentially two of these that are next to each other, one positive, one negative. Okay. So if we have an electric field that's eta over 2 epsilon naught and another one, and we add them together, right, you're going to end up with an electric field that looks like this. So it just gets rid of the 2, because remember the electric field from the positive plane points this way, and the electric field from the negative plane also points this way. And so you add them up and they add in the same direction. So instead of a half eta over epsilon naught, you just have eta over epsilon naught. Okay? And remember, just like with the plane, the electric field is constant inside a capacitor. Okay? So just a reminder, the electric field is constant inside a capacitor. All right? At least for a parallel plate. So